For the last section of your text, we'll get into graph theory next. We're going to look at find the area of something. Now, the problem is, can't make it that easy. There's not going to be a strict formula. We're not just going to find areas of trapezoids or triangles or things like that. Good news is we will be finding areas of rectangles. Bad news, to get there, it's a little complex. So, we've done this before. This should look familiar, where if you have a geometric series, you can write it as adding everything up, or you can write it as summation, and it will always end up equaling this first term divided by 1 minus the common ratio. Okay? You'll also see it written like this, where you allow that n value to go to infinity. Okay? Those at least look familiar? Okay. Now, we also have the general limits of a summation. So if you evaluate finite and infinite solutions, you end up using these properties here, these four. In other words, this is where you have I squared, I to the third, just I being some function. If you just have a constant, that's the easiest, just constant times whatever this number you're going up to is. So if you want the sum of the series of sevens, where you're going from 1 7 to 12 sevens, well, you just take 12 times 7. I use this formula, that one should look familiar, I squared and I cubed. Okay? And we also have this property. If you're taking the sum or the difference of two functions, and you're doing the summation of that, you could actually just figure out their individual summations, then apply the addition, or apply the subtraction. The other main property we're going to use, if any kind of multiplier you have, you can pull that value out in front of the summation as well. Okay? Now the reason for all this is for when we have problems like this one. Okay? And we'll make these sequentially a little more complicated each time. But for this, I have I squared. Now admittedly, this one you could just plug in the calculator, right? But if you didn't have the calculator, but you had the formulas, I squared is just this nn plus 1 2n plus 1 over 6. So for in this case, what's your n? 50. So you're going to take 50 times 50 plus 1 times 2 times 50 plus 1, all divided by 6. So what is 50 times 51 times 101 over 6? The formula is over 6. 2,550? Yeah, you got a little more work to do. 42,925. Okay. Now, Millie, get there eventually. Now, you could do this with the summation program on your calculator, right? If you go down to summation, go into sum, go in there, put everything in. But that's if you know specific endpoint values. If you don't, if you're just going to create a formula like this one, yeah, your calculator's not going to help you much. What's going to help you is those properties where I can split things out. Okay? I'm going from I equals 1 to n of I plus 3 over n squared. All this is actually just telling you the sequence. Okay? This is actually what the last term in that sequence is, or technically any term. If you want the seventh term, you just plug in 7 for n and for I. Okay? Now, so this is going to change over time. I'm just going to look at this part. I'm going to split it up using those bottom two properties here. Any terms that I can, I'm going to split in apart. Any multiplier, I'm going to try to pull to the front. So looking at this, the overall multiplier is the fact that this whole thing is divided by n squared. So I'm going to take that and put it out front. That's going to leave me with the sigma from I1 to n of I plus 3. But since I have the plus sign there, I can split that into two different sigma values. So I'm going to pull that apart. So I have 1 over n squared times sigma of the I plus sigma of the 3. Well, the 3 part's especially easy. What's sigma 3? Not just 3. So remember, I is going from 1 to n. 3n. It's 3 times whatever's up here. So this is 3n. This part, no. Because that I is constantly changing, you're going to use the formula for the constant back here, or not constant, for just I, which is n times the next term divided by 2. So I'm going to replace that with n times n plus 1 divided by 2. And the whole thing is times 1 over n squared. Okay? Now I just need to clean it up. So, I'm going to multiply through the top. I also want to add these two fractions, or this fraction and this together. When I distribute through the top, I'm going to have n squared plus n over 2. What do I have to change the 3n into? 6n over 2. So now I can actually add that together. So I have 1 over n squared times plus 7n over 2. And then multiply the 1 over n squared back in. So I have n squared plus 7n over 2n squared. Is there anything I could simplify? You can take a single n out. Because if you want to do it this way, just so you can see it, factor out an n, top and bottom. So the n's will cross off. Your actual answer then for this is n plus 7 over 2n. Does that make sense? Okay? So let's step it up one more. This wants you to find the limit of this series that then goes to infinity of the summation of 2 plus I over n squared times 1 over n. Okay? The process is actually the same as what's up here to start. You're just going to, at the end, make n go to infinity. Okay? So I need to clean it up. I need to get rid of the sigma. So I'm going to multiply and square all this stuff out first, just so I'm not dealing with the squared sign. When I do that, I'm going to get 4. I'm actually going to go over here with it. 4 plus, well, 2i over n plus another 2i over n is going to give me what? (4i over n), which I'm actually going to rewrite a little bit. I'm going to rewrite that as 4 over n times I. Okay, because I'm going to do more with it in a minute. I'm going to want that formatting. So I'm just foiling this part. So it's 2 times this plus another 2 times this. So that's going to be 4 of these. And then just rearrange a little bit. And then plus what? Well, that's not I as in -1. That's not as the square root of -1. No, not that I. So it's just going to be I squared over n squared. Or if you want, 1 over n squared times I squared. Now the whole thing is still times 1 over n, right? So then I'm going to distribute through the 1 over n. So I get 4 over n plus 4 over ni plus 1 over n squared I squared. All of that is inside the sigma. But the nice thing is that sigma, you can separate it out, right? Into multiple summations. So I get sigma of 4 over n, and actually I'm going to move the constant out front here. So I have 4 over n times sigma I. I'm going to move the 1 over n squared out front, so sigma I squared. Oh, I meant to distribute it. No, this should be 4 over n squared. Yep. I did it for the first, but not the rest. Sorry. It should have been. Whoops, not there. Sorry about that. You're right. The 1 over n would distribute to that. Okay? From here, now I'm going to use those substitutions. So what's the sigma of 4 over n going to change into? It'd just be 4. Because it's, remember, I is going from 1 to n. 4 over n times n. So if you want, you could also move the 4 over n out and put leave a 1 there. So it'd just be n. But yeah, you'll just end up with 4 for that. I'll go up to the right in a second. Here, what's the I going to get replaced with? N times n plus 1 over 2. And then the I squared, it's the harder one. Yeah, n times n plus 1 times 2n plus 1, all over 6. Okay, now, well, clean it up a little bit. 4 over n times n is just 4. Here, I would distribute the 4n and distribute the n squared at the same time. My numerator is going to turn into what? 4n squared plus 4n over 2n squared. That'll simplify in a second, but let's finish off this last part. Okay? So if I multiply these two together, then distribute the n, well, if I FOIL these out, what am I going to get? 2n squared, which will turn into n cubed because of that n. What for the middle term? 3n because of the n squared, plus 1 times that n out front. Yep. Now the bottom's just what? 6n to the third. Everybody good up to there? Questions so far? There's so much little stuff here that's easy to mess up something. Like forgetting to distribute the end of the right stuff. So, for this now, I'm going to leave these separate. I'm not going to try to combine them together because on top of this, I still need to apply the limit. This is S of n, or S of n, I should say. So I want to do the limit as n goes to infinity. But that limit can apply to each term, right? So what's the limit as n goes to infinity of 4? 4. What's going to happen to this? It could, but remember, if I just make this go to infinity, careful, this part becomes irrelevant, so you get 4n squared over 2n squared, which is just 2. 4 halves, right? Everybody remember this?
Yeah.
Here, these become irrelevant, which is 1/3. So overall, you're going to get 6 1/3, or 19/3 if you prefer. Easy enough? Well, relatively. Questions on any of that? Yes?
So, are we have to memorize
Those 4 formulas? Yes. But considering one of them C times N.
Yeah.
So you really have 3 to memorize. Now notice though, what was the title of this?
Area problem.
Have we done area yet? No. So we still need to do the area. Now, we'll do some of it tomorrow. Looking at this shape, this is the kind of area we're going to want to find, the area of this shaded region. Okay? There's a way. Show you later. Because the problem is, you're going to also have to be able to generate the formulas, which the calculator will not do. Okay? So, if I want to approximate the area of this curve, well, I know how to find the area of a square, a triangle, trapezoid, those kind of things. We have formulas for that, right? But when this region is constantly changing size, I need to adapt for that. So what we're going to do is we're going to use shapes that we can know the area of to find the area of that shape we don't know. So if I look at this, I want to actually break this graph up into 5 rectangles. Okay? I want to figure out the area then of those rectangles. So if I have f of x equals 8 minus x squared, what's that graph look like? Parabola opening, down, y-intercept of 8. So if I graph this, okay, so here's where it starts. Now, I also want to be bounded by these regions, by this curve, by the x-axis, by the line x equals 0, and the line x equals 2. So that means I actually want to be between this 2 here and this 0, and in the first quadrant. So if I draw this curve, well, if I plug in 1 here, what do I get when I plug in 1? 7. What about when I plug in 2? 4. When I plug in 3? Well, what is it, though? Because I want to draw the curve accurately. -1. So the idea is my curve looks something like this. Yeah. Because of the scale, it almost looks like a line, yeah. My scale's not accurate. But, for this then, I want to take, you're right, I don't care about this part over here, but I want to look between the y-axis, this line, the x-axis, and that curve, and I want to find the area. So I'm going to split that up into 5 rectangles. Now, how wide are each one of those rectangles going to be? 2? Says 5 rectangles of equal width, and I want those 5 rectangles. Now, to make the math easy, I want to use the x-axis here. So I want to have 5 rectangles here, which would be 2/5. So I'm going to split this up into each one of these being 2/5, 4/5, so on and so forth. Right? So the idea is I'm going to come up here and then generate this rectangle. Come up here, generate that one, so on and so forth. Does that make sense? Now, is it going to be completely accurate? No, because of those gaps. We are going to approximate. That's not the same thing as guess. Okay? So, with this, how do I find the area of one of those rectangles?
You multiply it. You multiply the length by width.
Okay, so what's the width? 2/5. What's the length? Plug in 2/5 to your function. Right? So I would multiply these together. Now the thing is, that 2/5 here, is that always 2/5?
No.
No. Sometimes it's what?
4/5.
Or? So I want that value to continue to get larger each time, right? So what I'm going to do is actually do a summation. I want to take I from 1 to what? 5. And I want this to be I in there. You gotta do this technique. Okay? That'll literally stay that way on the test. So, well, if it was 100, I probably wouldn't do it this way. There's a bunch of different ways to do these problems. For this then, I'm going to plug that in. This is width of the rectangle times the height of the rectangle. And then the height is going to change depending on which rectangle you're talking about. And this will add them all up. So what I want to do here is replace this. So if I take f function, which is 8 minus x squared, plug that in. So instead of x, it's going to be 2/5 I squared. And it's still times 2/5. Okay? So I'm doing the sum of that. So this is where all that stuff from before comes into play. I'm going to simplify this out a little bit. I'm going to move this 2/5. You can distribute it through later if you want. I'm just going to move it to the front so I don't have to deal with it. So I can move that out in front of the sigma. This part is going to be times 8 minus, what's going to be 2/5 I squared? Well, what's 2/5 squared? 4/25. And inside I just have I squared. So I'm going to split it up into those pieces. Because what's the sigma of 8 going to turn into? 40, because it's 8 times whatever n is, and my n in this case is 5. Minus 4/25 times, now for I squared, yeah, so in this case it'll be 5 times 5 plus 1 times 2 times 5 plus 1 over 6, right? Simplify that. 2/5 of 40 minus 4 over 25. Here I'm going to have 5 times 6 times 11. The nice thing is, because you're over 6, what's going to happen? 6's are gone. You could do 55, or you could also do this 5 and 25. Cross off. So you start with 2/5 times 40 minus 44 over 5. At that point, look at the calculator. What do you get? No, not 31.2. 12 point what? 48. 12.48. Make sense? How will we make that more accurate? Why would doing more rectangles help?
Well, because then you have less of a drop down in height, you have smaller gaps.
Your gap will be smaller. So how many rectangles do you want to do? Okay, so if you want to be, go to infinity. So what you want to do for this, and this is what we'll look at tomorrow, you actually want the limit to go to infinity. Alright, but we'll do that part tomorrow. Questions so far, though? Okay.
Why is it 2/5 I? Like the function.
Because if I means I'm going to plug in 1 for that, and then I'm going to plug in 2, then 3, then 4. So that's 2/5, 4/5, 6/5, 8/5, 10/5.
Alright.
Okay. Anything else? Okay, the rest of the time is yours.